In this video, we're going to talk about how to solve a specific torque problem involving a table and a mass. So the problem states that the table shown below has a center of mass at a point 0.5 meters to the left and 0.35 meters up from the right table leg. So the first thing I'm going to do is I'm just going to draw where that is. I'm going to mark it as red, and I'm going to put it here. I know that it is a distance of 0.5 meters here, and that this is a distance of 0.35 meters. So this is the center of mass for the table. We also have a 60 kilogram mass that is placed on the table. And the question is, how far to the right of the table leg can you place this mass before the table tips over? So the idea is that if I keep moving this mass to the right here, that eventually the table would fall over. And it would rotate around this point here, which makes this point our axis of rotation. And so what we're going to do is we're going to try to figure out the torques due to that axis, or around that axis of rotation, due to the various forces that are acting on the table. So we know, for one, that we have our center of mass of the table, which is acting here and has a force, which is the force of gravity on the table. I'll call it Fg sub t. And of course, the force of gravity on the table is just equal to the mass of the table multiplied by g. And we are given the mass of the table as 10 kilograms. So this is a known value. We also have the other leg of the table here. So assuming that the mass, if there's no mass on the table, both legs of the table are supporting the table's weight, and this left table leg would be supplying a force upwards. Now, at the point that we are interested in, we are looking at the point just before the mass tips the table over to the right, which means that we are looking for the point where the force on this leg is actually 0. Because if I move my mass a little bit further to the right, the table tips over and this leg isn't touching the floor. And the point just before that is the moment where the leg of the table is not quite being pulled. The table is not actually flipping, but the table leg is not pushing up or not pushing down on the floor, right? It's just having a 0 force because the mass of the table acting at its center of mass is exactly counteracting, in terms of torque, the torque due to my ball. So this table leg is not going to be applying any force to the floor. The floor is not going to be applying any force to the table leg. And so this force here is going to be 0. The only other torque that is going to be acting on my system is that due to the force of gravity on the ball. And we know the mass of this ball or whatever it is to be 60 kilograms here. So this is the mass of the ball times g. And we can calculate these numbers out, but I'm not going to at the moment. I will just leave it in terms of variables for the time being. So now that we have all of our forces written out, what we really are interested in is finding the point where the torque due to the force of gravity on the table is exactly the same as the torque due to the force of gravity on the ball. And at that moment, the table will be at the verge of tipping over, but not quite tipping over. And then if we push the ball beyond that point, the table will tip over, right? So the equation that we're going to look to solve is that the net torque, so torque net, equals 0, which is equal to the torque due to the table plus the torque due to the ball. And our first step should be trying to solve and find an equation for the torque due to the table and the torque due to the ball, and then plug that into our net torque equals 0 equation and hopefully be able to solve for the position of the ball in the end. So the first thing that we're going to do is I'm actually going to redraw this picture, but I'm going to remove a lot of the excess parts to make it easier to see the geometry that we are going to be working with. So the situation that we have here is that we have our axis of rotation, and I've drawn simply the location of the two torque forces acting relative to our axis of rotation. So we have the force of gravity on the table and the force of gravity on the ball. I have also drawn the r vector, the vector that points from the axis of rotation to the location where the force is applied. I've drawn a separate r vector for the table, r sub t, and one for the ball, r sub b. Now we can try to find a value for this torque due to the table in a few ways. We could explicitly find theta using the information that we were given in the original problem, and then we could find sine theta and we could multiply it by r and the force of gravity, which is a completely fine way to go, and we have enough information to do that. But it's actually a lot faster if we notice a quick geometric trick. So the first thing that we're going to do is I'm going to simply draw out, as you always should, r vector for the table. So that looks like this. This is my r table vector. And my force vector, force of gravity on the table. And the angle that we are looking for is this angle here, theta, which I will put a subscript on to indicate that it is the angle for the table here. Now, this is where the tricky geometry comes in. So what I'm going to do is I'm going to label this complementary angle theta prime sub t. And it turns out that because we're interested in the sine only of this angle, the sine of theta prime of t is the same as the sine of theta of t. You can check this for any two angles that add up to 180 degrees, and what you'll find is that for some angle phi, which is just an arbitrary angle, I don't care what it is, that the sine of the angle phi is the same as the sine of 180 degrees minus that angle phi. And this is true for any angle phi, and since we can see that phi prime of t is equal to 180 degrees minus, theta prime of t is equal to 180 degrees minus theta of t, then this relationship must hold, and these two angles have the same sine, which is going to turn out to make our lives a lot easier. Now, here's the trick. If we look back at our initial picture here with r sub t in the force, if I draw a triangle for r of t, that is, I break my vector that points from my axis of rotation to the force, the point where the force of gravity acts on the table, I find that the side across from theta sub t prime is actually equal to r of t times theta of t prime. Which means that if I rewrite my torque due to the table equation, I get f sub g of t, r of t sine theta sub t, and I'm going to replace theta of t with theta of t prime, since these two things have exactly the same value for that sine. And you notice that this term here is just the distance from horizontally from the axis of rotation to the f of g, the force of gravity vector. It is just the x component of that distance, which you may remember from the beginning of the problem is a value that was given to us. That is the distance from our axis of rotation horizontally to the point where the force of gravity acts is 0.5 meters, which means that this component is just 0.5 meters. So we didn't have to explicitly find our theta sub t. We didn't even have to explicitly find our r sub t. We just could find, if we knew the distance perpendicular from our axis of rotation to where the force was applied, we ended up finding our r sub t times the sine of theta. And from there, we can just write down our torque due to the table as 0.5 meters multiplied by the force of gravity due to the table. And because this torque is attempting to shift or rotate our table in the counterclockwise direction, we call this a positive torque, because we call torques that attempt to rotate our objects counterclockwise positive, and torques that attempt to rotate our object clockwise negative torques. So this torque here is a positive torque, and we actually know all of the values because we know the force of gravity on the table and we know 0.5 meters. Let me just take a moment and generalize this this trick that we just did to any torque that we're interested in. Let's imagine that we have a wrench, and that wrench has some force applied to the end of it. And that force is being applied at some angle theta. So I've drawn my r vector here in red. I've drawn my force vector. And we, at the bottom here, you can see that I've drawn my r vector and my force vector from one location together, and that they make some angle theta between them. Now, in general, I can always write my torque as r vector times f vector times the sine of the angle between them. And if I was given the direction of the force and the angle theta, I could definitely find the torque that way. But what I can do instead, and this is useful for certain problems where I'm given some information and not others, I can draw this force as kind of a line continuing backwards, and I could do this continuing forwards as well. I basically just continue the force line, and I find this distance here, this distance of kind of closest approach of my force. The closest that my force vector, when I extend it as a line, gets to my axis of rotation at the center there, right? And of course, this line should extend all the way to the axis of rotation. Now, if I am given that distance RF sine theta, R sine theta, this distance here, then I can write my torque, which all I'm doing is rearranging terms. I'm not changing anything, right? But notice that this is just that distance. And this is simply a way of getting around having to find theta and having to find the magnitude of r vector in situations where you are given explicitly r sine theta, that closest approach distance, right? Which is exactly the case that we had here, right? We were given, if we go back to our original problem, we were given this 0.5 meters, this distance of closest approach. If I extend my force of gravity line down, right, that is the closest this line ever gets to my axis of rotation location. And so I can simply multiply the force of gravity, the mass of my table times g, by this closest distance, because that closest distance is given by r sine theta. Now let's try to use this same technique in order to analyze the torque due to the ball resting on the table. Now the question we're asked is, how far over from the table leg can the ball be placed before the table tips over, right? So let's assume that I have currently placed it at that ideal location. And the distance that we're looking for is the distance from the table leg, which goes straight up here, to the ball. So we're looking for this distance d, right? How far over can the ball be placed before the table tips over? But if we look at our r vector for the ball, this blue arrow pointing up and to the right, this r vector points from the axis of rotation to the ball, and the force of gravity points straight down from there. And if I use our new technique where I extend this force of gravity down until I reach the point where it is closest to our axis of rotation, such that these two lines make a 90-degree angle, I again find that this distance here, where this is our angle theta between r and r vector and our force, that distance is r of the ball sine theta, which is exactly the distance d that we are looking for. So it turns out that the torque due to the ball has a magnitude of d, the distance that we are looking for, times the force of gravity on the ball, right? Because this is magnitude of the ball's radius times the magnitude of the force of gravity on the ball times the sine of theta. And but our sine of theta times the radius of the ball magnitude is simply the distance d that we are looking for. And because this torque is attempting to rotate us in the clockwise direction, this is a negative torque. We have to manually insert that minus sign because we can see the direction that the torque is attempting to rotate the table. So now what we can do is we can go back to our original problem. That is that we wanted to solve this net torque equals 0 equation. We know that the total torque must be 0, and so let's plug in the values that we have found for our problem into this equation to see what we get. So we know that the torque due to tension is given by this 0.5 meters multiplied by the force of gravity on the table. And we know that the torque of the ball is equal to this distance, which is what we're interested in, multiplied by the force of gravity on the ball. So we know that the net torque equals the torque due to the table plus the torque due to the ball, which is 0.5 meters times the force of gravity on the table minus d multiplied by the force of gravity on the ball, where these are magnitudes. And this must equal 0. Solving gives us d multiplied by the force of gravity on the ball equals 0.5 meters multiplied by the force of gravity on the table, or our distance is 0.5 multiplied by the ratio of our forces of gravity. And given the numbers from the beginning of the problem, we can simply plug those values into this equation and solve for a distance d that the ball can be pushed across the table before the table will flip over.